Okay, so let me begin. First of all, I want to emphasize that this is a framework and not a model. It's a system for building models, student models specifically, of course, um, and doesn't represent like PFA or AFM, some specific sort of way to do it. The only thing specific about it, of course, as Bob was, or Robert was just, or Rob was just saying, is that it's logistic regression. Um, so yeah. So let me get my slides moving. So I kind of like to think of this in terms of an erector set metaphor. If you're older, you can see how old these kits were. You're probably familiar with the erector set where you have all these parts and they kind of have the same schema. They have the same distances between the bolts and so forth, so you can connect them up easy, and you can make all sorts of different projects out of it. And so I wanted to do that for logistic regression knowledge tracing, which I think is kind of a broad class of models, as I'll argue here in a minute. And just to kind of describe the organization today, so I'm going to give, we have about 20 slides. Luke is going to take the last couple, and then we're going to go into a series of examples where we show you what's going on with each of the examples a little bit. We could take questions about the different models and how you can make changes in the models and so forth. And so it's not meant to, it's meant to be kind of like mostly a seminar, but a little bit of a tutorial. If you want to go to the example page, you may have already downloaded some of the data, and so you could follow along later on too, and I'll talk about that again more later. So anyhow, an erector set for student models. So first, a little bit of basics. Luke was pointing out to me that we might get some cognitive modelers here, and so I want to kind of point out the difference in my mind, at least, between student modeling and cognitive modeling. Student modeling is typically focused on prediction of outcomes, more attention to model fit, more attention to maybe using the model later to put it into some sort of running system. Whereas I think cognitive modeling is more attention to the cognitive processes and actually understanding what steps the brain is going through or the mind is going through. And maybe less attention to fit, more attention to the pattern of results of the effects. Is Zoom blocking my slide? Did I just fix it? Yes, okay, thank you. So yeah, less attention to fit, more attention to the pattern of effects, I think, in cognitive modeling. There's a lot of overlap though, and I've worked in both, kind of moving from cognitive modeling to student modeling because I was interested in applying things and getting them running in the classroom. And I felt like cognitive modeling, while it explains the same things, is kind of a step too far to really implement them easily. So that's why I've kind of moved towards student modeling more. And we'll look at what the data means in terms of student modeling here in a minute as well. So first of all, in student modeling, it's become ubiquitous to talk about Bayesian knowledge tracing, which was invented by Anderson and Corbett in the 90s, working with the early work on the cognitive tutor systems at Carnegie Learning, the work that rolled into their products later on. Of course, Carnegie Learning's products still use Bayesian knowledge tracing, I think in almost all cases still. And it works very well, but it's not especially easy to use or accurate. It's based on this idea that you have 4 parameters, a learning rate, initial learning, a guess, and a slip parameter. So it's relatively simple. One reason it's tractable to implement in a system as large as the systems that Carnegie Learning operates with the cognitive tutor is, having a simpler model is kind of necessary if you're going to be able to make it work with thousands of students. Maybe we can, achieve greater complexity as we, develop the technologies, but it's been difficult to control these things in running systems with students. using, trying to do adaptive practice. That's one of the things I specialize in, is focusing on the schedule of practice and how you can extrapolate the schedule of practice from these sorts of models. Today, I'm not going to be talking about practice scheduling. I'm going to be talking about how you understand the student data with these logistic regression models. So after Bayesian knowledge tracing in the history, we could talk about the additive factors model. And so that's where we start talking about logistic regression. And it's an obvious transition between item response theory, the simplest kind of one parameter item response theory where you have difficulty and student ability, and models of student learning. So you still, like the simple IRT, you have intercepts for student and knowledge component, not item in this case. Here we group items into knowledge components, which actually goes back before AFM. And so if you want to dig into the history of this, some of my review work has talked about, earlier work with IRT and how it actually grew out of that. So this model, it's a lot easier to use than Bayesian knowledge tracing, but it's not very adequate in a lot of ways because it only has this linear slope coefficient describing the effect of the opportunities to learn. And so if the student has 3 opportunities and the coefficient is 0.3, they have a 0.9 logit, because it's logistic regression, 0.9 effect on their learning there. That goes on top of their intercept and their for the student and their intercept for whatever knowledge component they're working on. And that's the additive factors model. It's these additive factors of the student's ability or knowledge and the difficulty of the knowledge component, and then the final additive effect of the learning for each prior opportunity that the student has had to learn it. So going on from that, I had come from the cognitive modeling tradition, and so obviously that model wasn't very adequate to me. And I could see right away that, the importance of testing effects and whether you get it right or wrong with a test is going to have a tremendous amount of information to predict future learning. And so I was thinking about a way to add that into the model. And of course, the obvious way to add it in and keep it logistic, make it adaptive. I'm sorry, I have this backwards. Keep it logistic, make it adaptive, because I wanted to make it adaptive like BKT, but I wanted to keep it logistic like AFM. And so this PFA model has been cited 460 times. And basically what I did is it just count the 2 outcome types separately. So in other words, I count the successes and failures for the knowledge component. Rather than counting the learning attempts, I just count the successes and failures. And so that was a big improvement, of course, over not counting the successes and the failures. And so that was one step along the road to those adaptive logistic regression models that are enabled by logistic knowledge tracing more generally. And so then there was kind of this march of the variance triggered around a little bit very quickly after I published the PFA paper. And I think I'm missing some variants actually here, but there was a decay version. This is where you weight the successes and failures depending on how many trials they were in the past. And so that's like exponential weighting. It's fairly easy to compute. And then, that was adapted into RPFA, which you do that same sort of exponential weighting based on how many trials in the past it was. And then you, except you're doing it for a proportion. And so you're taking the successes weighted by their recency divided by the total opportunities weighted by their recency. And so that was a nice improvement in fit over PFA. Then there's also, of course, people investigating, individual differences with this sort of model. IAFM, I think that was Liu and Kadinger maybe, and that one was, all of these are cited actually in the README for the package in GitHub. So if you want to dig into the citations, and of course in the package description, it actually cites the paper that describes the LKT in its entirety as well. So anyhow, IAFM then adds a slope for each KC for the knowledge components for the student. In other words, students have their own learning rate. And so the learning function is not just for the learning of the knowledge component based on how hard the knowledge component is, but it's also based on how fast the student learns. PFA difficulty is one that I did recently with my graduate student, Mung Sao, who's here right now. And that one's neat because here we're taking not the count, but we're taking the sum of the prior difficulties, and then we're actually conditioning the prior difficulties according to an inverted U-shaped function, so that prior performances at an optimal level of difficulty get more credit than prior performances that might be either too easy or too hard, or too easy, depending on which way you have the graph organized in your head. And then, this extends to other things besides these student models, perhaps, because, there's this PPE model that is kind of in the cognitive psychology realm, but it's kind of military educational technology is what they're working on there under some Department of Defense grants, I believe. And so that's called the performance prediction equation. And it's a lot of same in my own case, coming from the ACT-R computational modeling school, working with John Anderson there at Carnegie Mellon. But here it's not done in ACT-R, it's done in logistic regression. And so they have this 4-parameter formula that allows you to calculate practice effects, spacing effects, and forgetting effects all together. But of course, one of the things that makes it so nice to add to this system is that it doesn't include adaptivity. And so, by combining it into this system, you can use, those mechanisms that they built without adaptivity in an adaptive context, kind of making the best of both worlds. So here's my little, shameless plagiarism of Tolkien, right? One ring to find them. And so the idea here is that without a master program, each of these methods has to be hand tooled. And so if I want to compare, how variants of these methods work, I have to code up each one by myself. It's a pain in the arse to redo for each data set and to build these by hand each time. And that's what I had been doing. And so I wanted to build this tool for my own lab, actually, to save time so that I could, if I want to do a number of different comparison conditions to whatever I'm doing right now, it's easy to build those comparison conditions and describe why the one I chose is better and so forth. And now it's going to be easy for you to do that. Use the many variants and discover what model models your data best, I think. Hopefully, by the end of this, you'll actually believe that. So one ring to rule them all. So this gets into the logic behind LKT, kind of in a little bit more depth to start here, is that it provides us a greater flexibility. And so you can describe any of these prior models in terms of LKT terms. Using the framework, just like you could with any good erector set, you can build these prior little contraptions. But you have more flexibility, because what you can do is you can match any component. Like you can have intercepts for the students, or you can have learning for the KC, or you can have knowledge tracing for the student, or you could have spacing effects for the item memorization. You can have all of these different components that you can choose specific features for, and the feature then determines, how the component is interpreted. And so, for instance, some of the features are line AFM, line suck, and line fail. And line AFM is the one for the additive factors model. And so when you ask for intercepts for the student, intercept for the KC, and then line AFM for the KC, you have AFM. Similarly, if you ask for the student KC intercepts, and then you ask for the line suck, which stands for line successes, and line fail, the linear effective failures, you have the PFA model. And so, it becomes more transparent what that means to match them up when you see the actual code in the examples, because the code in the examples actually has a one-for-one pairing of each component with each feature. And there's kind of the assumption that when you look at these features, they're always within a student, except in certain specific cases. And we can get into that if you were thinking about what I said. But you could fit. I guess what I'm saying is that when you count the observations for a KC for a particular feature, you usually do it for each student. So you could count all of the observations across students, but that wouldn't make any sense. And so a lot of the things that are going on behind the scenes here to count up things, like to make these sums of prior opportunities, are kind of built so that it all works together. And I think that, like, as I said, when we get to these examples in just a few minutes, you'll see that. So in short, there's kind of three different kinds of features. There's static, like intercepts that don't change, and basically it's just the intercepts that are static. And there's, I suppose, covariates could be static too, because you can have those as well, and we see an example of that later. And also they can be dynamic, which means they're changing. And so in a perfect example of the additive factors model, it's not adaptive, but it does change the prediction with each opportunity. And so I call these dynamic versus adaptive. Adaptive means it's going to be a function of the actual outcome, whether they got it correct or incorrect. Whereas dynamic might be just because it changes with time, like recency is not static. It's dynamic, but it's not adaptive either. At least simple recency, the simple recency function of the time since the prior trial, which is actually two different recency functions. We'll kind of see that also later. So this is applied per level of the component or overall. And what that's saying is that, you could get one learning rate for all of the KCs, or you can get one learning rate for each KC. Or you could get one learning rate for each item, or you could get one learning rate for all of the all of the items to be the same. So you can do interactions. That's the covariant interactions. And also, I want to emphasize we're happy to add your feature to the package if it makes sense, or if it's part of a publication and you think it's a compelling thing for us to want to have in there. If you actually sent the code for the feature, it might be a rather quick addition, and even better if you'd want to collaborate with us and help build this project to be able to handle more. And then I just want to make a plug for the technology too, because one of the reasons why it was built, in addition to having to not have to hand tool it, was because I was really seeing that GLM in R was slowing me down, and I wasn't really clear that I needed to move to Python, but maybe I would have if I hadn't had these other solutions, which has been to use kind of super fast R packages. And that includes liblinear, which is built on C++, I believe, and data table, which is far more efficient and fast than the built-in data frames of R. It also uses sparse matrices to represent absurdly large model matrices. So, I think the largest we've worked with is more than 10,000 parameters and 2 million rows of data, which of course wouldn't even turn over. It would give you a memory error right away if you were using a data frame with GLM and R. Okay. And so continuing forward with these slides, I think, let's just see. I'm more than halfway through with my part. And yeah, okay, so we're making good time, I think. Oh no, it's done that again. It switched my screens. Just 1 second while I maximize it again. Oh, now it's put it on the other screen, conveniently. there's more than one way to solve a problem like this. I'm just going to unplug my other screen. Okay, now it's on the right screen. But now I only have one screen, so I got to organize my widgets. Okay, backing to where we were. So there is an example data set that's located in the package. And so when you do library LKT, you'll see this, this example data set available. It's just the variable sample LKT. And you could immediately run some of these simpler examples on that. However, this sample data set is so simple that it doesn't have time in it. So it's more like some of the prototypical example data sets for some of these earlier educational data mining projects where you only have like about 4 columns of data. You have the student, you have the outcome, you have the KC, and there's one other column, but the item identity. But yeah, and so this sample data set's in there for use, and I'm just making you aware of that. And so then this is the process of how you use it overall. If we think about it as a pipeline, get the data, make sure it's correct, make sure it fits the format that we'll be seeing here and is in the example data. Consider the components given the data. And so here we're talking about, what are the different levels that you want to predict? Do you want to use the KC to predict things? Do you want to use the item to predict things? Do you want to use the student to predict things? And so what are the different levels of the separations of the data that are going to be kind of dependent measures, or not dependent measures, but independent measures. And then consider the paradigm to detect the features. I think that it's useful to think about whether you're working with something that's memory-based or whether that's something that's problem-solving or categorization. A lot of the memory terms aren't going to be relevant if you're working with problem-solving is probably the biggest takeaway there. And I wouldn't be surprised if you add forgetting into some of these problem-solving data sets, you wouldn't see much of anything in terms of improvement of the model. Okay, and then finally consider parameterization. This is whether you want to have one parameter for each level of your component or whether you want to have one parameter overall for your component. Of course, this isn't an issue for intercepts. If we're talking about an intercept, of course, we're fitting one intercept for each level. And so that goes without saying. And then also there's this issue of the nonlinear parameters, and some of these features that we're going to be describing are nonlinear, and so they have a nonlinear parameter, and that's solved with a kind of a nested optimization with inside LKT, where it has to actually use the optim function in R to try many different parameters in order to find out what nonlinear parameter is optimal given that configuration of the logistic regression model. And so that's a few details there. And so then here, I just wanted to talk, before I get into showing all these models, about the different things that we can add into them. All paradigms are going to have individual differences. They're going to benefit from student and item variability terms. Typically, I do this with either fixed intercepts, which I've been mentioning, where you have a fixed numeric value representing each student or each item or each KC. Or I do it adaptively, where what you have is it's analyzing the function of a function of the prior outcomes in order to estimate the intercept on some level. These can be used together, but often if you use fixed intercepts and you have good data, then there's nothing less to adapt to because the fixed intercept captures all of the variability or most of the variability. However, because a lot of these adaptive tracing functions are focused on the recency and tracing recent outcomes, it is true that you can get some additional benefit from the adaptive tracing with the intercepts too, because it'll catch fluctuations in attention and things like that over the course of student practice. And so one thing to think about in terms of this is that you have trade-offs too. You know, if you have a model term that's tracing knowledge and using the outcomes, well, it's going to be highly multicollinear. It's going to be highly correlated with the number of observations. And so, you know, as you get it right more and more, that predictor of learning as well as the predictor of tracing are both going to be affected. And so the PFA model they originally created, what it does is it has successes and failures be two separate terms. And it has this dilemma in kind of the worst way, because when you get a success or a failure in PFA and you get the increase due to that success or failure, you don't know whether that increase is due to learning or because they got it right, you now know that they know it better. And so it's a question of whether the terms are identifying variability due to the learning, or whether they're identifying variability due to the performance. And the PFA terms do both. Some of these newer terms allow you to split it out better. And that's another advantage of LKT, is that in theory, at least, you can separate out, you know, a tracing feature that is based on prior outcomes with a learning feature that's based on just the accumulation of outcomes. Though that's difficult unless you have fairly nice data too. So all paradigms have learning as well. Typically, it's ubiquitous. You know, if you have repetitions, you'll find that the second repetition of something is better than the first repetition, unless it's kind of a paradoxical situation. Perhaps if they had no feedback on the first repetition, then it wouldn't happen. But that's not a situation we see very much in learning data. So really, learning is ubiquitous. The curvature of the function may be important. And so we have a lot of different curvature functions. And we also have curve functions with forgetting and spacing. The one many of you, or a few of you might have seen before, is log count, where we just take the 1 plus the count and we take the logarithm of that, and that creates decreasing marginal returns. And so that each additional practice then, sorry, question? Oh, just somebody had their mic on? Okay, no worries. Yeah, and so that creates a decreasing marginal returns to practice, which is often what you're looking at when you're trying to get a curvature in a learning function, because depending upon the paradigm, of course, each practice oftentimes has less effect than the previous practice. And so you kind of have this improvement in model fit that's kind of consistent with the log count in a lot of the data sets I've seen. Then we also have nonlinear features, recency. There's two kinds. It's both trial-based and temporal-based. We find it's very powerful in both forms. Me and Luke, when we've been working with a lot of data sets with these models. Forgetting, you know, this is going to be key if you have a memory paradigm, basically. Spacing effect, again, for memory paradigms. Maybe the spacing effect mechanisms we have in right now are not really built for interleaving effects so much as spacing, because they're temporal based. So I don't know that we have one that's fully tested for interleaving effects. So if you had a feature in logistic regression that described interleaving effects, well, we might love to have it. And so as I was saying, it's easy to add features. If your feature excites us, we can add it for you. And then finally, the system allows transfer learning, and this can be useful for categories where you have multiple items and you want to think about how item learning transfers or the learning of the category transfers to the items or something like that. And also, of course, is good for problem solving, because I think of problem solving as essentially a transfer situation where the items within the KC are transferring to each other. But you can have multiple levels of transfer, because what's going on here is that you can have you can feed in multiple KCs, because you're not restricted with the number of terms you can have in these regressions. And so each KC then can be at different levels, and so they can group. So you could have an item KC, an item K, that's supposed to say KC, an item KC might have two KC columns, for example. Oh, I'm sorry, I'm speaking too quickly. An item might have two KC columns, for example, and I wrote this slide just last night, and that's why it's garbled. And so what that's saying is that the prediction for that item then depends on both columns, or could depend on both columns, depending on how you declare the model. And we have an example of that coming up too. And so performance could then be a function of the multiple columns, as I was saying. So this is kind of a rich example before we get to the equations. And actually, it's the last thing I have to say before Luke has a couple of slides. And so what we see here is, the multiplication table, and we can imagine, we want to build some system to teach third graders this, and we might consider how do we want to build that model, and so I was analyzing the task, having done this before also for K-12 Corporation as a consultant, analyze the task and describe what features we would want and what components those features would go for. And so Logitech then is one of those performance tracers, and it's actually the log of the successes divided by the failures. And that's why we call it Logitech. The DEC means that it also has those successes and failures are decaying according to a specific function. And so it's basically the recent log successes divided by failures, which creates essentially a synthetic intercept for the student based on their prior performance. And we actually use, I would suggest in this case, using that for both of the KCs as well. And here I'm proposing that maybe there's two KCs involved, two basic KCs. First of all, the multiple KC, in other words, 8, 16, 24, 32. This is the KC that groups items that share a multiple. And so, in fact, now that I analyze the task a little bit more, there's a kind of you might have the multiple for the first value and maybe the multiple for the second value as parts of this model. Then you could have the tracing of the item, because of course there's a lot of memorization going on here, and that people learn these item by item as well. And so the Logitech at the item level would capture that. Then some of them are more difficult than others, and so I would have an intercept for each of the item KCs. An item KC is basically I'm making the identification between the concept of the item, or the construct of there being items as kind of the lowest level of knowledge component. And so when I'm talking about that, I'm talking about the performances for the individual item grouped together, only with performances for that same item grouped together. And then finally, we could add a memory term, because this is the sort of thing that probably is memorized to some degree. And so we could track learning, spacing, forgetting on top of these other effects. So with that said, I want to turn it over to Luke, and then we'll start with the examples. We could take a break for questions too, but then go with the examples. Take it away, Luke. Thanks.
Thanks, Phil. I'm not sure if I have the ability to get this next slide. Okay, thanks. So what I'm going to talk about is kind of how easy it is to make new features when you have this framework. And so I'm going to describe a pretty popular feature, proportional decay, originally introduced by Galliard and Golden, 2015, and talk about how the kind of the functional form of that feature lends itself to some other properties that I think that I've used that I think highlight how good it is to have this general framework. So recency weighted proportional decay, or PropDec in LKT, is basically a recency weighted moving average that helps track student knowledge states And just as an example here, we have a practice sequence where a student is initially incorrect a couple of times, those 2 zeros there, and then starts to be correct, right, 3 times in a row. So implying that there's been a change in their comprehension of the material, right? And so here in the figure here, I have a typical cumulative mean, so like the average of the prior trials in black, and you can see it's going up slowly, but it's not intuitively like probably tracking like the actual level of ability that the student has now. Now prop deck, you have a parameter for basically how heavily you weight the more recent attempts. So you can imagine you could have your average only be looking at the prior couple of trials, right? So it's exponential, so it's not going to just weight the last couple of trials, but it's going to weight them more heavily. And so, for example, the red line, the dark red in the middle there, that's a parameter D of 0.5 for prop deck as an input feature. And so you can see it's kind of going up more steeply. And then a D of 0.25, that's light blue there, that's really like weighting the more recent trials more heavily, right? And as you can see, so that's going to probably track with the student's actual ability better, right, when there's sudden changes in knowledge states, right? And so it's a pretty simple concept, right? There's 2 input features. There's the practice sequence of their correct or incorrect at whatever level of counting you're doing, an individual item level, the concept or KC, or overall for the student, right? You do the next slide, Phil. But now I'm going to talk about how being able to see all of these functions together in the LKT framework led to me making a new feature that's really just tweaking this prop deck feature, right? So just a couple of changes led to being able to track a very different ongoing process in these adaptive learning systems. So the new feature, instead of putting in the correctness of their practice sequence, I'm putting in something else. I'm putting in the predicted outcome minus the actual outcome. So there's like a probability of correctness that your learner model is going to have. And then there's going to be the actual outcome. It's not always going to be right? And so what we're measuring now isn't student performance. It's the discrepancy between the model's prediction of the student and the actual performance by that student. And if that value, that like running average of the discrepancy is not around 0, if it's positive or negative, you're over or underestimating that student in a systematic way. Because something we haven't touched on too much yet is when you fit a model to prior data, and then you're going to generalize it into the future for other students, you don't have parameters for those students, right? You're going to need to use population parameters like, like average learning rate, for example. And that might, work on average, right? But students are going to vary around that mean, and you're going to have some systematic error, right? And that's what inspired this feature, right? It's like, oh, so instead of tracking performance changes over time, I'm going to track systematic model error over time. And so if the value is positive, we're overestimating that student, we're going to have some problems because we might, decide that they've mastered content too early, or maybe take too long to decide they've mastered content. The student's going to be bored, right? So this is relevant in practical situations, right? And so we're basically rethinking what we're adapting to with this feature. So instead of adapting to their knowledge, we're adapting to the model making errors. So all we're changing, and if you look into the code, you're going to see that this feature I'm calling error deck is basically a copy paste of prop deck, but I changed what gets inputted and a couple of other minor things. And the parameter is basically deciding how much of the prior discrepancies you're using to estimate this systematic error, right? And so this visualization here is a very simple example of what I'm talking about. So you might have a really simple linear AFM model or something like that. And that's the black line. So it's like assuming a certain learning rate, as practice accumulates, it's assuming probability of correctness. Right? But now a real student is going to diverge from that in some way. So that's the blue line here. Students learning a bit slower than expected. We're going to have consistent discrepancy over time if you take the prediction minus the outcome. And the dashed red line is if you incorporate this error deck where you're tracking, how consistent is the discrepancy over time. We're consistently overestimating their learning. We're going to adjust for that. So it's this prop deck, except the input is this difference, this prediction minus outcome. And the feature ends up adjusting for that systematic error that the model is going to make. And it's pretty prevalent because people have to use, overall average learning rates represented as, coefficients when they're predicting performance for new students, right? We don't have student level parameters, right? So this is just an example of a new feature that we've made that I think was partially inspired or facilitated by the fact that we were able to see kind of the machinery of all of the features that are typically used in learner models kind of in one place, right? You're really able to play with all these individual features, right? And if you look into the GitHub code, you can see like exactly what the function is that like makes, proportional decay work. And I think it kind of reminds me, like my analogy for this, it's kind of having a general framework for this that allows you to build all of these features. It's kind of analogous to how when students first learn statistics, they think of things as kind of atomized, like, oh, it's a t-test, oh, it's an ANOVA, but eventually, hopefully they learn this is all part of a general linear model, and this is kind of the same. It's not about, EKT versus AFM versus PFA, right? It's about using specific features to deal with certain educational contexts, And I think this error deck feature is kind of an example of how beneficial it can be, to have it all in one place to allow kind of research or experimentation. I don't think I have any other slides for this, so that's it.
Excellent.
Yeah.
Thanks. Okay. So I muted myself. That was silly. So let's switch to R here. I think probably do one example in R and then take a break. And so first of all, though, I want to post this link here in chat for the mailing list. That's just a Google sheet. If you want to put your email and your name there, we can make sure to tell you about the next release because we do discover bugs, of course. I may as well share my video again. Good. And so also I wanted to mention that the data set we're going to be talking about is described in the LKT paper. And so, we mentioned the LKT paper. Maybe we should be more transparent about where that paper is located too. And so if you go to the, if you actually just look for LKT on CRAN now, you'll see it's there. And my screen is shared, yes? No, my screen is not shared. Say, somebody's telling me my screen is not shared, probably.
I can see the brand.
Oh, am I shared? Oh, no, okay, I'm misreading my screen. Okay, very good. Yeah, so here's the actual manual, and that's kind of what I wanted to point out, as well as the data set. And so if we go to GitHub, we can see the data set that I'm going to be showing here in R, because I'm going to switch to R here in a minute. And so, yeah, here. And so you can see the data set here now with data. I think you should be able to download this because it's a public project and get the full data set if you don't want to use the small sample LKT file that we have. Okay, and so then going over to R. So what I just did in R is I ran these preliminaries. You can see the preliminaries, of course, in the examples that I have posted here on GitHub. which may be a little easier to read, and there's nothing kind of dynamic about these yet. So you can see here, it's loading in the data table package, as well as the LKT package, and then loading in the data, creating a data table. Let's see here. Ah, yes, okay, I got myself sidetracked. Thank you. So when we go to the package here, I meant to say this paper here, the RX5 paper. Thank you, Philip. Which is the not yet published paper that I was mentioning. Thank you, Luke, for putting it in the chat as well. It's so confusing trying to navigate all the windows on Zoom sometimes. So back over to R, where I've just loaded in the data, and there's this function called compute spacing predictors that needs to get run for any components like the default KC, the default knowledge component that I'm going to be using a lot, in order to get the time values. And so you can see the duration column and the CF ... time columns were necessary for those in the just prior to those two lines there. Yeah, like I was saying, we can see that in here a little bit easier. I'm just saying this final line here is the one that gets these is necessary for a few of the features, was the key point. And so the first model then is our additive factors model, which is the model that's built into the Pittsburgh Science of Learning Center data shop. This is a fixed effect version. LibLinear doesn't do random effects. You know, we're looking at different ways, you know, that we can enhance the project. And so if you think of, if you know how we can do random effects using LibLinear, love to hear it. So what that means is that these are the optimal parameters, and they're not based on some sort of, you know, shrinkage to a distribution like random effects would be. This is just your standard logistic regression that's being optimized for the additive factors model. You can see it outputs a little bit of information about the model it's putting in during the process, and it gives you McFadden's R-squared and the log likelihood. There's a number of other values that are in the variable, and so we can run that over here and see what those are. Just run that first model.
Also, the you can see that part of the input to LKT here is a vector called components, which is student ID, KC default, which maps to the features vector, which is basically what's being done at that component level. So like the student level for the first index of component is having an intercept computed for each of those students according to the first index of the feature vector.
Right, so there's 477 or 478 students. So that's generating a numeric intercept for each of those students. Similarly, for the KC default, we're getting a numeric intercept for each KC default. I think there's 72 of those. And then we're also getting a numeric slope for each of the KCs for the prior opportunities. Line AFM is the one for the additive factors model, because the additive factors model is prior opportunities. That's what this feature means. It means using prior opportunities. And here we're applying it for the KC in the standard method it's used for additive factors. Yeah, thanks for getting me going on that, Luke, because that was exactly the detail that we needed to talk about next, is that pairing of the components with the features. And essentially each of those pairs is one term in your regression. And then you could add on a global intercept by the interc command. And actually, when I was looking at this model earlier, I was realizing to myself that the intercept was redundant, because if you have intercepts for all your students and your KCs, you don't really need one overall. And so I can set my global intercept to false here, rerun it. I should get the exact same fit, and I do. It's slightly different because of the fitting process in the LibLinear. You're not going to get, you know, to like you know, 7 decimal places or something, as you can see here. It's almost the same. When you do a different matrix, the solution is slightly off. There's also ways, though. You can send in the linear parameters if you want to have it be a little bit more insistent to find the absolute optimum. You'll see less variability in this sort of effect here. But so what's most people are interested in then after they run the model is looking at the coefficients. And those are just stored in one of the many objects that are within the output value that is created, including the coefficients, the model in terms of the linear model, R squared, the prediction vector, and this is the predictions in terms of probabilities for all the observations in your data set. Often people are looking for that, so you want to, you know, you're probably interested to know where that is, because if you're going to be graphing your model or something like that, or analyzing your model fit, you might want that prediction directly. But what we want to look at right now is the coefficients, just to confirm that the design of the model is what we would expect. And so here we can see the intercepts for the KCs, and I kind of breezed over it earlier, but these are fill-in-the-blank sentences. Each fill-in-the-blank sentence has 4 different fill-ins, and so they're kind of grouped. And there's 18 sentences, each with 2 versions, each with 4 different items taken out of it. And so you can see the difficulty, like this one here. This first one is a negative 0.26 coefficient, so it's quite difficult. We can scroll down, and after we scroll through all the KCs, intercepts, we're going to get to the intercepts for the, actually it looks like I had that wrong. There's 144 of them. Yeah, here are the student ones then. So you can see the students vary in their ability as well. And then finally at the end, I think it's at the end, we'll see the learning rates. Yeah, so here's the line AFM parameters indicating the positive learning rates for each one of these responses. It is a pretty well configured data set. You know, there's more than 100 observations for each student, and so that's why we see consistent learning rates even at the lowest item level. Let's see here. You had a question, Luke? You were saying something there? Or you were replying to somebody?
Yeah, I was replying to Robin's question about how the parameters are estimated.
Yeah, right. That's an interesting point, Robin. I think it's actually quite relevant because some of the models imply that we have that information, specifically like the PFA difficulty. It needs the prior responses, probabilities, in order to predict the current response. Right now, we simulate that by running the model twice. If you have a running system, though, like the MoFax system that I have this model in, running and delivering practice to students, it actually uses the probabilities that were previously generated in, and so it does do it one step at a time, doing each new response in sequence. But here it is a simultaneous fit. Good notice about the details of what's going on. But yeah, so you see these linear parameters then for each of the items. If it was close to 0, of course, that means an item is very difficult or almost impossible for people to learn. Right, and I think that got us right up to 1. How about that? I didn't even time anything. And so you can see, I'll just give a little foreshadowing here. We'll go through, look at performance factors analysis, how you do that, how you do this difficulty sensitive model here, how you do recent performance factors analysis. This one here is recency tracing with 2 different kinds of recency, both temporal as well as trial-based. This is the one that includes 2 different types of KCs simultaneously. This one here is the RPFA with recency powerful combination. This is the performance prediction equation base for, we're not going to have to, or we're not probably going to want to talk about all these, but we'll go into some depth on a few of them, certainly. Then covariates, individualized additive factors model, where we use covariates to get a linear slope for each student that applies at the KC level. Is there a question? No? Okay. And then finally, how to trigger the cross-validation to see that, you don't have too many parameters after all these parameters we've been finding. And so we'll see you all back at 1:06 if you haven't already heard enough. Thank you very much for your attention so far.
Oh, yeah, and if anyone has any questions, feel free to ask. I'm going to be hanging around here for the next few minutes before he restarts.
I'll just go ahead and ask a question, but you can also wait to answer it later or something like that. I'm kind of generally curious, how many observations per knowledge component is really required for each student. Like, I mean, an example you gave, like in the slides, of like 5 problem attempts. Is that a realistic number, or is that a minimum number? Could you even obtain reliable estimates with 5 observations? Or if you have any kind of thoughts or guidance there on like how many observations you'd be expecting. And then the other question that's sort of related to that is there a way to obtain sort of confidence intervals or confidence estimates around the coefficients for each of the coefficient outputs that you showed before? So that is a general question. You don't have to answer now before you go for it.
No, yeah. So the example I was giving with the 5 was just a toy example to illustrate those features. So if you were trying to say, build a model with reliable coefficients to then use in a running system later, you would want to have got more than 5 trials per student. Like let's say you're trying to estimate a coefficient for, the amount that the probability of correctness increases as a function of the number of prior successes. You'd want to be getting more than 5 trials per student for a lot of reasons. For one, this initial process of fitting a student model, you're going to want to have, many cases of students getting more or less correct, or you're going to have to experimentally manipulate maybe how many attempts they get so that you can potentially observe some kind of nonlinearities as a function of the number of practice attempts and successes. And so 5 would probably not be enough, right? Because you probably, that there can be some, still some benefits to additional practice even after someone's successful multiple times, right? And as far as like how many trials would be required at minimum, I think it's going to depend on the particular like features you're using. Some of them are going to be noisier than others, and are going to require different experimental setups in order to collect data to fit the model. Like the recency feature, for example, you would need to have maybe multiple like multi-session experiments to be able to actually reasonably fit that parameter. So I think a good example of like how many data points you might need will be, we have this paper we published in MPJ that was basically showing how you could create like a student model, an adaptive instructional system from scratch, from initially collecting some data, parameterizing a model, running a simulation, and then testing it in an experiment. And we're basically doing the base 4 model here, which has like 4 parameters, and we wanted to get intercepts for each item. And we ended up collecting data from how many students, like 150 participants doing about 40 minutes of practice over 2 sessions. And to make sure that the parameters were reasonable, like the spacing effects, decay effects, we had students practice lots of different like 3 different retention intervals over time. So coming back for a test at different intervals. And that required, I think it was a couple hundred trials per student to parameterize all of that. And it was 130 students. But it's going to vary a lot on based on the variance of the thing you're trying to estimate, like the parameter, like what kind of feature it is. Some of them are noisy.
I kind of like to think of it though as, if it takes too many students to detect it, it must be a fairly small effect. And maybe it's not worth investigating with that many students.
Right, like we collected a lot of data in that case because we wanted to be able to detect like 2- and 3-way interactions between spacing and practice attempts and things like that. And those are reliable effects, but they're not super huge, those higher level interactions. As for you asked about the confidence intervals, we're using liblinear that uses that does some regularization as it fits. And so to get confidence intervals directly from that, I think you'd need to do bootstrapping.
In other words, having LKT generate confidence intervals is a moving target.
Because
we don't have that yet, and it would be great if somebody knew how to do that and could just tell us how to do it too.
I think the answer is bootstrapping, because there isn't like a.
I meant more like a recipe. Yeah, I think you're right, but I meant more like more hand holding would be necessary perhaps than just having bootstrapping. Yeah,
GLM is slow, but if you have, I guess one way to get some confidence intervals would be to estimate, like to create all of the features with LKT, but then fit a GLM, and then you would get a confidence interval because of the assumptions GLM makes. And that's one way to do it.
Great. People are inspired to ask questions. Do we want to ask more questions right now? Are people thinking of a few things that we could talk about? Or should we just start talking more about a few of these example models? Okay, it sounds like we want to see some example models. I guess my screen is still being shared, and I've turned my other monitor now because I don't have to fight with PowerPoint for it. So I can see the chat pretty easy too. So this is, I'll show them over here before I run them because it's bigger and I think probably easier for you to see. And then I'll run them over on my computer or on in my R actually. So here you see performance factors analysis, again, the fixed effect version, not using random effects. And you can see that, again, as Luke was describing earlier, we have this one-for-one pairing between each of the features and each of the components. And so the LKT function, we're requesting a student ID, an intercept for each student ID, an intercept for each knowledge component, default knowledge component, a linear function of successes for each knowledge component, a linear function of failures for each knowledge component. And this is the first introduction of the $, or no, I meant second introduction, but maybe I'll get into it a little more in depth. This is, again, using the $sign notation. And the $sign notation is what creates an individual coefficient for each of the knowledge components rather than overall. And since it's quick to demonstrate, I think I'll go ahead and demonstrate that too here when I show this. Also, you might notice at the end of this example, we actually stash the prediction back into the data set. And this involves Robin's question a little while ago about whether it computes it simultaneously. Our next model is in the diff core feature is going to require those predictions. And because it computes the predictions simultaneously, it doesn't have them unless you simulate a situation where you would have them by running another model first and saving them. So going back though, up to the performance factors analysis, and then just going over to R to run it. And so here we have it, and we can just click go. And you can see it ran fine. It fits a little bit better as we would expect than AFM. Maybe not surprisingly that it doesn't fit that much better actually, but the variability in student outcomes is kind of large. And so we don't see this huge improvement when we add this simple adaptation. We just see a small improvement. Actually, the intercepts capture a lot of the variability in a situation like this because students vary quite a bit in their ability, and the items vary quite a bit in their difficulty as well. If we took those terms out of the model, it would not nearly be as strong seeming as it is with a McFadden's R squared of 0.3. And so again, we can view the result to see the coefficients. And again, that's just the model. You could name the variable anything, obviously, but I just called it that earlier. And so we see I asked for a global intercept. Probably shouldn't have done that. I can take that out here in a second and rerun it. Here we see our intercepts for the KCs. If we scroll down a bunch, we'll see our intercepts for the students. Scroll down a bunch more. We'll see here are our failure linear effects. And then even we're gonna maybe have to open this up a little bit to see the headers. It's not cooperating with me, the interface. There we go. So anyhow, I guess I'll ask you to trust me. Sometimes the ordering of the factors here, these bottom ones are actually the effective successes. You can't see, I guess you can see that when I my mouse over, you can see that it's just listing the successes at the very end of the parameter name. So it's inconvenient to see in the display. And so this is, our full PFA model then, taking out that redundant intercept. Let's go ahead and do that. So that redundant intercept is the global intercept that you call with the true false here. But also let's take out these dollar signs to see how that affects things. Because, I've said that that creates one of these linear parameters as a function of the prior successes, as a predictor. And you get a coefficient for each KC. But what does it look like if you don't get a coefficient for each KC? So we can run that. Well, the first thing we'll notice is that it doesn't fit nearly as well. It goes down to 0.28 because we no longer have that capturing the individual differences in the learning rates of the items. And so that's one effect. But we can also see it when we look at the parameters. Just scroll back up and run this command again. Here we can see now that we just get two parameters for line suck and line fail for KCs. And what that's showing then is that, we get more of a benefit or more of a increase in our prediction, shall we say, when we get a success in our prior data compared to when we get a failure in our prior data. And so you can see how much the logit value goes up before the prediction of the probability is computed then here with the coefficients. Any questions about this model? Okay, it is kind of boring, I agree. I complained about that. It was too simple earlier, right? This next one I like a lot more because it has a lot better implications for learning. In fact, you can really see it in that example. So if I were going to use this model to schedule practice, it just tells me that I want to get successes all the time. What good is that? That's clearly not really correct. It's crediting successes with information, and it's not really just learning in there. And this is that trade-off between what the parameter means. It doesn't really identify with the construct very well. So this next model then tries to correct that by having the learning here for successes be a function of the difficulty at the time of those successes. We can actually fit a parameter to that to change that value if we wanted to. There's different versions. No, wait, no, I'm getting confused. That's a different one. This one is just specifically, this combines them. So this is the probability plus or minus the probability squared. And if you compute what, take 0 to 1 and you take probability minus probability squared, you get an exactly inverted U-shaped function that says that 50% correct is where you learn maximally. And so that's what this is saying, is that whenever you get prior practices close to that middle range of difficulty, you're going to learn more for them. And as they're closer to a situation where you wouldn't have got it right, or would have definitely got it right or definitely got it wrong, you're going to learn less. And so this model is useful because it allows you to make inferences about what's going to be best for the student after you parameterize it. Also, it's the reason why we had to save this probability here. We had to stash the prediction because when we're doing this on the fly in a tutoring system, we have the prior probabilities. It's easy to do. But when we're doing it with this simultaneous model fitting, we don't, because we have all the probabilities all at once at the end. And so we really have to run the model twice. And so that's what that's about. So specifically, as it was saying, this allows us to make inferences about what the optimal probability is correct, because we can actually split this into two terms too. We don't have to just fit one coefficient to the probability minus the probability squared of the prior correct responses. We could fit a coefficient for the probability and a separate coefficient for the squared term in order to place our optimum value at whatever is actual. And so you can actually solve for the optimal value for your learning here using the two-term version of this. Of course, you have to have data that really characterizes the paradigm well, and so it does require that, obviously. So are there questions about this one?
Just to reiterate, so this, in case it wasn't clear to people, fitting this model requires having probabilities for all the prior attempts. You fit a model to the data and then have a column of the predicted correctness probabilities, which is our operationalization of difficulty here. And then you could fit this model. Yeah,
and that's why, like I was saying, that's why we needed to do this in order to run this one, which we haven't run yet, right? Which though we just stashed that difficulty last time we ran it here. And so we should be able to run it now. You see, it says here that there's a note that it says that it needs that too. And so when we're making models like this, we wanted to, kind of inspect them on some level as well to make sure that things make sense. Because if we have like negative parameters for things, it may be that we have a model that's overfit on some level. And so that's another reason why you can look at the coefficients. Here we can see that the diff core is a very strong positive value when we fit it to the data, indicating that it's not being, somehow overfit, and it would find some paradoxical negative result. This is kind of your basic check that you want to do when you make these sort of models. Is the learning rate for success is positive? Is the learning rate for failures less than that? When you get items more correct, does the model predict that the student is going to do better? If it doesn't have these basic features, you probably have too many parameters and things are starting to kind of be too multicollinear. And that's kind of like just some advice on how to build these things. Also happy if I trigger questions at any point. Recent performance factors analysis was Galliard and Golden, as Luke mentioned a little while ago. It was one of the inspirations for some of the work on LKT at first, because it had done very well to fit the data, and so I wanted to replicate it for a comparison condition. And so wanting to use it probably more than once in the future, I've tried to make a flexible system to do that. Here you can see that this is, I think, the canonical version, except now that I look at it, actually, I think that the way that Galliard and Golden did it was slightly different, because I believe that they had a coefficient for each of the KCs in this case.
I think they also, at least in the paper, they fit student level intercepts, and the proportional decay feature was at the KC level, not the student level. In this example, I think you're doing both student and KC level, which, no?
No.
Oh yeah, you have the intercepts.
Yeah.
Okay.
This is standard RPFA now that I added the dollar signs. So I think what Luke is kind of pointing out is this the ability that I haven't really highlighted too much, because I've been looking at these previous models that other people have done, which are not adaptive at the student level. I've been using the intercepts at the student level, but we could use PropDec at the student level. Like this if we wanted to. Of course, because PropDec has that decay factor, we would need another parameter here. 0.9 works pretty good in most cases, though you can optimize them if you want, like I had said too. And so here is kind of what Luke was suggesting at first he thought we were doing, which is to have the adaptivity using the PropDec feature both for the student and for the KC, which would be a more powerful model if you want it to be adaptive, because it doesn't need to know the student ahead of time to get a good fit. If it gets just a few trials of the student's data, it's going to react to that, just like the error-dec function that Luke was talking about, and improve the fit for that student for the rest of the performances in a sort of a tracing function. Okay, so there's that one. Let's look at a few more here and go over where it's easier to see.
Sorry, I'm having trouble. Please try it in a little while.
Alexa thought I was, oh, there I did it again.
Here's something I found from WikiHow. To think more effectively, try
I'm
approaching
just gonna unplug her. Anyhow, she always wants to get involved. So this is recency tracing with Logitech. Logitech is like PropDec, except as I said, it's the log successes divided by failures instead of the proportion successes divided by the total. And so this traces, in this case, you can see it's tracing the KC, but we also have a recency term. And so here we have, this is an example of recency tracing in two different ways, because the Logitech traces the recency of the successes and the failures in terms of trials, whereas the recency term uses the time in seconds since the prior trial and does a power law decay function. So it takes that time, say if it's 20 seconds, here the parameter is 0.5, so it'd be 20 to the negative 0.5 would be the contribution of this figure after 20 seconds. 40 to the negative 5 would be a negative 0.5 would be the contribution of this feature after 40 seconds, and so forth. And so here we see it's tracing this temporal recency as well as the recency of the performance. I think this next example then shows how you can use multiple components simultaneously. And so here we have the KC default and the KC cluster. The KC cluster refers to the sentences And so it groups together the 4 responses that are for the same sentence. Whereas the KC default is just the individual items. And so here we can see that we're using Logitech for the KC default. We have recency for the KC default. And so those are going to be like tracing the items and tracing the recency of the items. But then we're also using the performance for the sentence to trace the sentence. And so if an item is shared in a sentence, if you get another response for that sentence correct, you're going to get more learning for that sentence. You can imagine this might go for different problems in a category or something like this in some other learning paradigm like problem solving. Questions are welcome, of course. I have a few more I can talk about, of course, too. So this is an example of how you find optimal parameters. And so in the prior models, I've just set the parameters equal to fixed values, but this one has the fixed parameters equal to NA, comma, NA. First of all, it's useful to point out that the number of parameters is just determined by the features. And so, you know, the reason why there's 2 parameters in this model is because PropDec 2 requires 1 and recency requires 1. And if you use these features, it becomes very, you know, there's just a few within each category, and you can look those up in a table in the paper to know how many features each one has. And so that's how I knew that I was going to need 2 features, but I didn't know what they were. It starts out with a value of 0.5. The system is kind of set up to assume a parameter default range between 0 and 1, and that's been working well for us so far, though it might not work for all models. But you can see it starts out with that value, and there's this solver iteration for many steps, and then it finally ends up with optimal values. And so in this case, we can see that the estimates of 0.5 and 0.5 would have been wrong. It's actually a little bit larger for that in terms of the recency is not so important. As the value gets lower, recency is more important. So the recency is not quite as important as 0.5 for the PropDec. And then in terms of the temporal recency, the decay is actually slower at 0.32 than the original value of 0.5. You can also set seed values if you don't want to start with the seed values of 0.5. Here's the performance prediction equation. In this example here, I actually combine it with the adaptive Logitech term. And so I have this 4-parameter PPE model, and then the 1-parameter Logitech in order to make an adaptive memory model, a memory model because of PP and adaptive because of Logitech. Here I do have fixed intercepts, so it's kind of assuming I know these subjects and items ahead of time, but that's not necessarily required either. I could you know, change any of these things. That's, of course, the whole story of LKT on some level. Is the flexibility to search the model space. Base 4, similar to PPE, doesn't work quite as well. I made up base 4 in comparison to PPE, but PPE is very, very flexible for all sorts of patterns in the data. And so you can decide for yourself whether that's a good thing or a bad thing. And then covariates is another feature. In this example, I actually just have covariates for the unit name. And so what this is doing is you can see the covariates row also matches 1 for 1 with the components and features. And by having the 3rd covariate be level unit name, I'm saying I want this line AFM term to be interact with the unit. And so in other words, there's going to be a different learning rate for each unit. Individualized additive factors model, IFM. And so again, this is the fixed effect version to distinguish it from a random effect version. And here what we're doing is we're saying that the, you know, it's basically the additive factors model, but we're saying that the learning rate for each student is different. And so, they either learn faster or more slowly than the average. And so here we have two learning terms for KC default. One that's just the learning based on the difficulty of the KC, and another that's a covariate where you have a function of this, which is an interaction with the student. And so that captures the IAFM model from the literature that other people created. And finally, we get to cross-validation, which illustrates and is perhaps a nice way to wind up the presentation portion of this, is because it illustrates the hazard of fitting too many parameters. And we can see that we have two different models: simple AFM minus student intercept, and then complex AFM minus student intercept. And as you might imagine, the cross-validation of the simple one goes better because it doesn't, it's less tendency to overfit. And so in this simple one, we actually just have a difficulty value for each KC. That's this KC default intercept. And then we have a single learning slope for all of the KCs. They're all going to be learned according to the same function, all separately, but it's just that the amount they gain is the same for each KC from the previous repetition of that KC. And we're going to contrast this model. Actually, there you can show that I actually this $sign here is redundant. You don't need to add a $sign to intercept, as I think I mentioned earlier. But this $sign here is not. This $sign here is going to give us a different learning slope for each of the KCs. And if we compare the fits of these two models, we see that the McFadden's here and the log likelihood correspondingly, because the McFadden's is computed from log likelihood, it's just easier to interpret. It's much better for this model that's more complex. However, you see when you look at the mean of the McFadden's from the cross-validation here, which I output right here and right here, that there's virtually no difference. And this is showing that the extra fit we're getting by adding all those slopes to the additive factors model in this second example is really only buying us a very trivial benefit in terms of generalizability. And so we don't want to get caught up in believing these McFadden's values or these log likelihoods too much, because we always could be in the position where it's caused by just adding a lot of parameters, and cross-validation saves us from that trap.
How many parameters does that add in that second model? Is it 144 additional?
143 actually, because it had one in the other one for.
Yeah, so that was not worth it. Okay, good example.
Yeah. Okay, well, thank you for sticking out to the end. I see that we retained 75% through the whole seminar, so I'll count that a victory. But that also we haven't had a lot of questions, and now we have a lot of time for questions, or we could be done early if we want. So feel free to ask difficult questions or easy questions, or no questions at your leisure. And I certainly give you some time to frame them if you want to think about it.
Hello.
Hello? Somebody on an open mic.
Summer's in full swing now. A lot of people they're filling out that waiver. Well, some are working from home, I guess.
Okay. Well,
Phil Grimaldi raised his hand.
oh, okay. Where I see.
Oh, sorry. I should have just jumped in.
Yeah. There's few enough of us.
I'll also turn on my video because why not?
Sounds great.
My question will be more basic, just because I'm still trying to wrap my head around the whole performance factor analysis idea. Earlier in the presentation, you said this is, in many ways a natural extension of IRT. When I'm thinking about, so for example, like in PFA terms, when you're talking about estimating a learning rate, is there like a translation from, so like in IRT land, we might estimate like a student's understanding with like a theta estimate. Is it fair that like, is my understanding correct if we were to say like a learning rate would be like a change in that theta estimate, or is it something
Yes,
different?
it's a change in this. It's a change in the theta that's specific to the KC.
I see. Okay. So is it practically, I mean, how is it doing that? Is it fitting like a logistic model, estimating data at each point and then measuring the change? I'm just kind of curious how.
Well, it just has it has predictors, right? And so in this case, there's two categorical predictors: the item and the student. And then you just simply what the feature does is it runs a count across each student for each item. And so I create an index for each student for each KC. And then for that index, I take the cumulative sum of the successes or the cumulative sum of the failures or the cumulative sum of the opportunities, and I lag it one so that it's prior values. And then so that lagging then means you use the prior values along with the identity of the student, the identity of the KC. You use the prior count of successes for that KC for that student, the prior count of failures for that KC for that student, the weighted prior count of, the recency weighted prior count of failures, the recency weighted prior count of successes. Does that help?
It does, yeah. That makes a lot of sense.
Great.
Philip, we got a question in the chat too.
Yeah. Could you suggest how to best model student ability and item difficulty in a setting where the students are doing a sequence of practice problems, 10 in a row, and they get immediate feedback plus hints, and even repeated attempts are allowed? The student ability can clearly increase from one practice problem to the next. Item difficulty seems to be problematic to evaluate because of mostly fixed order for instruction. Oh, okay. So this is a big problem, actually, fixed orders, because it makes it really, really, really hard, if not impossible, to infer difficulties. And so this is a real problem. You can try to do workarounds, perhaps, like not model item difficulty would be probably the workaround. But even then, typically the way these instructional sequences are created are by putting the easy items first and the hard items later. And so it's not even like it's yeah, I'm not sure if it can be done, and this has led me to believe that in situations like this, if you want to do item difficulty, and in fact, if you really even want to know your learning function, you have to gather some data that's experimentally controlled or randomized. Because if you don't, I mean, maybe somebody else has a resolution to the problem that I don't know, but that's where I'm at.
There's a recent paper by Neil Heffernan and some other people in which they try to use like educational data sets that were collected like within a system as alongside experimentally collected data together to try to get difficulty estimates and things like that. But they didn't, at the end of the day, I think an important takeaway of that paper even was they still needed the experimental data to get the initial parameter estimate, and then the large bias data set where there's like fixed orders and things like that was used to like help reduce the confidence interval around it, right? So getting experimental data, it still seems to be necessary.
Yeah, or even randomized. I mean, because if you have some items in your, if 10% of the time, if you have enough data and 10% of the time you're doing it random, that's going to be enough to compute your difficulties.
Yeah.
And so if you have a fraction of your items that are randomized, this could solve the problem, I suppose. Another thing that's interesting in here is that estimating student ability can be contaminated by the instructional sequence, because if things are easy early on and hard later on, it makes it difficult to estimate whether the students are getting it right because it's easy or because they're good. And so it causes kind of a contamination in the whole system if you have no randomization at all. Great questions.
I guess to the point, that last point, Phil, around item presentation order, are you or have you used a PFA or models like this for doing adaptive item selection, and do those produce better estimates?
Well, I'm using, I don't use PFA, I use LKT models for.
Okay, yeah, LKT, sorry.
Because PFA, as I was saying, is kind of rudimentary, and the extrapolation to an adaptive sequence is pretty poor. I mean, I think that, there's two ways that we're going with the adaptive sequencing work is I think one being sensitive to, item variability and trying to target the optimum level by picking items that are at the right point. Whereas the other one is more about monitoring where those items should be at in terms of their memory characteristics and whether they're being forgotten down to a level where practice will be optimal again. And so it's not focusing on the items and the difficulty so much as the effect of the memory. But in both cases, I'm incorporating this sort of, that inverted U-shaped function of difficulty theory. I'm basically working with a fairly strong assumption in a lot of my adaptive scheduling right now that there is an optimum between 100% correct and 0% correct. It is never, according to the model I'm using right now, optimal to get 0% or 100%. If that's not true, the model's wrong, of course, for any particular paradigm. I could try to unpack that too if I got lost, got people lost. Okay, well, thanks for joining us today. If you, there should be the link for the mailing list, and if you didn't see it, and feel free to send me an email and I'll put you on it. And anybody who you are talking to, or your collaborators or whatever, who want to be on it. So unless we have some final thoughts, thank you so much for being my audience today.
Yeah, and feel free to reach out to, I guess, either of us if you try to use LKT and encounter any problems.
Yeah, we got it on the GitHub. We got an issue tracker, and I plan to be tracking all the issues that inevitably occur with software. And I hope that this package will be following me for the next 5 or 10 years and can become a community resource. Okay, thanks. Bye.
Thanks.
And thank you, Luke. See you later.
Yep.